Welcome back, Chemistry 30. This is the MS2.1 molecular shape and molecular polarity section. So determine whether a molecule is polar or nonpolar based on its geometry and the individual bond moment. So we kind of take what we did with MS1.7 and we are just simply adding one more thing onto there, and that's determining whether or not a molecule is polar. So polarity. Earlier we discussed bond dipoles. A dipole occurs when two equal and opposite charges are separated by a distance. When two atoms share electrons equally due to a difference in electronegativity values, a dipole results. And by that I think I said equally, but I meant unequally. So, for example, here we know that there's a fairly big difference between the electronegativities between these two. So F would contain those shared electrons more often than H would. So what happens is that we would get this side being slightly negative and this side slightly positive, which we discussed earlier. HF is a polar molecule due to unequal sharing of electrons between atoms. What about larger molecules? So it's easy to see when you have two atoms, but what happens when you have like a tetrahedral shape? So that's what we're going to look at over here. The picture on the bottom right represents the molecular geometry of CO2. Yes, it seems like we've drawn this one quite a bit with a double bond here in between the C's and the O's. So yes, we've drawn this multiple times. We could simplify it like that. When electronegativity values are taken into account, it can be seen that the central atom experiences a pull towards the oxygen atoms. But as you see here, since it is linear, it's almost like a tug of war. We experience a pull in this direction because yes, the electronegativity of carbon is 2.5. The electronegativity of oxygen is 3.5. So that gives us a difference of 1. And that difference of 1, if you recall in your electronegativity table, means that it is a covalent bond. It's not big enough to be ionic. It's a covalent bond and it's in unequal sharing. So we have a negative side and a negative area there. But what happens here, the sum of both forces will be 0, because you can think of it, if I'm experiencing a pull in this direction and an equal and opposite pull in this direction, it is going to balance each other out. They're going to balance each other out. In physics, we would call this vector addition. If we have these two vectors, start here, a pull to the right, a pull to the left, we end up at our starting point, so the net force is 0. So CO2 is considered to be nonpolar. So just because a molecule possesses polar bonds, such as here, so here we have a polar bond, and here we have a polar bond, because there is a pull in a particular direction, and that difference in electronegativity is greater than 0.4. But as a whole, the molecule may not be polar. It has to do with the symmetry of that molecule. Do those forces cancel each other out? If the molecule has some kind of symmetry, then it may be nonpolar, as we'll see on the next page. If we look at a water molecule, here we go. Lone pairs of electrons make the molecule unsymmetrical, therefore polar. So if we have electrons that are non-paired, such as in this case, this could be water, that kind of indicates that it may not be symmetrical. So the picture on the left represents water, and of course oxygen has an electronegativity of 3.5, hydrogen is 2.1. So yes, if we subtract those two, yes, we definitely get, let's see, 1.4. That's going to make it covalent, but unequal sharing, right? When electronegativity values are taken into account, it can be seen that the two hydrogen atoms experience a pull towards the oxygen. Now here, because it's a bent shape, I have this, so if I was to start here, again, even if you didn't take physics, you can kind of see how this vector addition works. We have this arrow, which is pulling up in this direction. Then this arrow, which is pulling up in this direction, so that's our final. So you can see there is a net force. We don't end up at our final, or we don't have our final spot being equivalent to our initial spot. So we will have a pull kind of upwards. Because we have this pull upwards, we have this pull upwards, so overall it's going to be a pull upwards, making this slightly negative and this slightly positive. Notice these arrows here, that I didn't mention it, but the arrows kind of indicate a pull towards the negative region, and of course what's left behind? A positive region. So it almost looks like an anchor tattoo, but what it's meant to show is that the arrow is always pointing in terms of the pull towards the negative, and a positive region is left behind. So that's what's being shown here with this one. So you can see positive region left behind and a negative region up here. So when electronegativity values are taken into account, it can be seen that the two hydrogen atoms experience a pull towards the central oxygen atom. The sum of both forces will result in a net force greater than 0. H2O, therefore, is considered polar. It does have a pull in a particular direction. There's no cancellation there. By adding the individual bond dipoles, one can determine the overall dipole moment of the molecule. Now, the following figures illustrate polar and nonpolar molecules containing polar bonds. The numbers are electronegativity values. So here, we just have two atoms in this linear structure. Of course, if I subtract that, I get 0.9. So that is a polar molecule. There is a pull in a particular direction. Carbon tetrachloride. This one's interesting. I have a pull out in this direction, pull, pull, pull. So they're all nonpolar bonds. 3 subtract 2.5 is 0.5, which is bigger than that number. But as we would see, the downward pulls of these is balanced by that upward pull. So this is symmetrical. It's a symmetrical molecule. And a symmetrical molecule means that everything will cancel out. By symmetry, we can turn that molecule, it would look exactly like this. Same thing with this one. If I twist it 120 degrees, this one's now at the top, and this one's now to the bottom left, etc. 4 minus 2.5 is 1.5, so it's definitely polar bonds, but overall it's nonpolar because these downward pulls that look like this are counterbalanced by an upward pull here. So again, it's a symmetrical molecule, and it's going to make it nonpolar when all is said and done. Over here, ammonia, NH3, so there's a pull towards the end, pull towards the end, pull towards the end. That N is slightly elevated, so it's a slightly upward pull, upward pull, upward pull. So that's going to be polar because it's non-symmetrical. Okay? And this last one, it looks a lot like this one, but it brings another idea into play. CH3Cl. We have H, H, and H, and Cl. At first glance, you may say, oh, it's tetrahedral, it's symmetrical, it's nonpolar. But guess what? It's polar because the outer elements are not all identical. This one isn't. This one's Cl, which has a way larger electronegativity than carbon or hydrogen. So what we end up having here is a slight pull in this direction, virtually a nonpolar pull. But in this direction, 3 minus 2.5, that's 0.5. So we have a fairly strong pull in this direction. That makes it polar. So that's another little tricky thing you have to look at. Symmetry and the outer molecule, the outer atoms that are attached to everything. Now you're likely asking yourself, how am I going to know, how am I going to remember this? I didn't take physics, I don't know vector addition, I don't know force addition, how do I know what cancels? Well, we can make a little summary on this chart that you have from earlier, the molecular geometry chart. If you take that out, there's something that we can do here. And I'm going to insert it right here. So we'll say when outer atoms are identical, this can be used. So we have P, which is going to be representing polar, and NP, which represents nonpolar. All right, so we have that happening. So when we have now, so we'll go through here now a linear. So if these outer atoms, just like in CO2, if they're both oxygen, we saw that it was nonpolar because it was symmetrical. So we can write nonpolar. In fact, with all of the ones that have no electron lone pairs, those are all going to be nonpolar. Of course, when the outer atoms are identical. As we saw in this previous example, you have to be careful if you're dealing with different atoms, Because even though this is tetrahedral, this one's so much more electronegative than the other ones, there will be an overall pull in one direction. But for the most part, if we're talking about identical, nonpolar, up and down cancel, and this equilateral triangle will cancel each other out too. Down here will be nonpolar as well, because into the left, out to the right will cancel with out to the left, into the right. So nonpolar. And this one's going to be nonpolar as well. So that kind of takes care of a lot of them. Now, a bent molecule, we should also say when electronegativity is large. I should say when difference, sorry, I'm kind of changing what I'm doing here as I go along. When the difference in electronegativity is large, and when the outer atoms are identical, we can use this schematic. Because again, we're looking for electronegativity difference of greater than 0.4. If you look back at your electronegativity table, you'll see that. We kind of numbers that we use there to figure out whether something's polar or not, polar covalent. This will be polar if the difference is big enough, because there will be a pull that's not balanced. This will be polar. Bent again will be polar. The seesaw shape, even though the axial ones may be balanced, these ones here will not be, so it's polar. A T shape will be polar, because even if this up and down pull are neutralized, we have this sideways pull. Linear, that is going to be nonpolar. So when we have a linear shape plus lone pairs of electrons, believe it or not, that's going to be nonpolar. And this one here will be polar, because even if these cancel each other out, we still have this one down here. And then this one, it's very similar to one that we looked at earlier there. Very similar to this one, and it's going to be nonpolar, because all of those will cancel each other out. So we can use that to figure out if overall a molecule is polar or not. All right, I think we'll stop the video there, then we'll come back and do some examples with this.